Yes, Articles 240.100 and 240.101 of the National Electrical Code are applicable to the situation. Yes, there is a tap rule for over 600 volts. According to Section 240.21 burn, an overcurrent device protecting a transformer rated over 600 volts shall be permitted to be placed on the secondary side of the transformer provided the primary is protected by an overcurrent device of equal or smaller rating. There is no specified maximum distance between the overcurrent device and the transformer. However, the overcurrent device should be installed as close as practicable to the transformer to minimize the risk of damage to the transformer or conductors in the event of a fault. If a new feeder is added and requires protection, the existing feeders may not necessarily need to be upgraded unless they are also supplying overloads. The National Electrical Code requires that all feeders be protected against overloads, meaning circuits carrying continuous loads, and short circuits, meaning circuits carrying fault currents. Firstly, add an overcurrent device to the 2.4 kV secondary side of the transformer as per Section 240.21 burn with a rating appropriate for the available short circuit current. Secondly, calculate the available short circuit current on the 2.4 kV secondary side and ensure that the chosen overcurrent device is rated to safely interrupt the fault current. Thirdly, install the overcurrent device as close as practicable to the transformer. Fourthly, check if the existing feeders need to be upgraded based on their current ratings and the loads they are supplying. To elaborate further, when dealing with a 3750 kVA transformer stepping down from 12.4 kV to 2.4 kV, the protection and installation must strictly adhere to the National Electrical Code to ensure safety and prevent equipment damage. Let's break down the key aspects. Firstly, the primary protection is provided by a 200 ERBA style fuse, which the question suggests operates at 400 amps before melting. However, the actual melting point and time current characteristics should be verified from the fuse manufacturer's data to ensure appropriate protection. Secondly, the secondary side at 2.4 kV currently lacks a main disconnect or overcurrent protection device. This is a significant concern because it leaves the secondary conductors and connected equipment vulnerable to overloads and short circuits. The existing setup includes 4 feeders, each approximately 30 feet long, supplying metal-clad motor starters, with the largest motor being 1000 horsepower. The plan is to add 2 additional 350 horsepower motors, one running continuously and the other used for short-term operation until the first can be shut down. Now, let's address the specific questions and recommendations. The applicability of National Electrical Code Articles 240.100 and 240.101 is indeed relevant. These sections cover overcurrent protection for systems over 600 volts. Section 240.100 generally outlines the requirements for overcurrent protection, and 240.101 provides more specific details for conductors and equipment operating at these higher voltages. The tap rule for over 600 volts is addressed in Section 240.21b. Specifically, 240.21 burn allows the overcurrent device to be placed on the secondary side of the transformer, provided that the primary side is protected by an overcurrent device of equal or smaller rating. This means that if the primary fuse is rated at 200 amps, the overcurrent protection on the secondary side must coordinate to provide equivalent or better protection. Regarding the maximum distance of the protection device from the transformer, the National Electrical Code does not specify an exact maximum distance. However, the general principle is to install the overcurrent device as close as practicable to the transformer. This minimizes the length of unprotected conductor, reducing the risk of faults causing damage to the transformer or conductors. Installing it as close as possible ensures that any fault occurring in the conductors between the transformer and the overcurrent device is quickly detected and cleared. As for whether adding protection for the new feeders will require upgrading the existing feeders, the answer depends on the existing feeder's capacity and protection. The National Electrical Code requires all feeders to be protected against overloads and short circuits. If the existing feeders are adequately sized for their current loads and are already protected by appropriate overcurrent devices, they may not need to be upgraded. However, a comprehensive review of the existing system is necessary. This review should include, firstly, a load calculation to determine the total load on each feeder. Secondly, a verification that the feeder conductors are sized appropriately for the calculated load, considering ampacity derating factors for ambient temperature, conduit fill, and other relevant conditions. Thirdly, confirmation that the existing overcurrent devices protecting the feeders are correctly sized to protect the conductors according to their ampacity. Fourthly, an assessment of the short-circuit current withstand rating of the existing equipment to ensure it can handle potential fault currents. Based on this information, here are detailed recommendations. Firstly, add an overcurrent device in the 2.4 kV secondary side of the transformer. This is critical for protecting the secondary conductors and connected equipment. The overcurrent device should comply with Section 240.21 Bone of the National Electrical Code. Secondly, calculate the available short-circuit current on the 2.4 kV secondary side. This calculation is essential for selecting an overcurrent device with an adequate interrupting rating. The interrupting rating must be greater than the available short-circuit current at that point in the system. Thirdly, install the overcurrent device as close as practicable to the transformer to minimize the length of unprotected conductor. This reduces the potential for damage in the event of a fault. Fourthly, check if the existing feeders need to be upgraded based on the current ratings and the loads they're supplying. This involves a detailed load calculation and conductor ampacity verification. To elaborate on calculating the short-circuit current, several methods and tools can be used. One common approach involves using software that performs short-circuit studies, such as SKM Power Tools, ETAP, or Easy Power. These programs allow you to model the electrical system, including the transformer impedance, conductor lengths and sizes, and source impedance to accurately calculate the available short-circuit current at various points in the system. Alternatively, a simplified hand calculation method can be used, although it may not be as accurate as using software. This method involves using the transformer's impedance and voltage ratings to estimate the fault current. The formula typically used is fault current equals transformer secondary voltage divided by transformer impedance. However, this calculation should also consider the source impedance and conductor impedance for a more accurate result. The overcurrent device selection is a critical step. The device must have an interrupting rating sufficient to handle the calculated short-circuit current. Common types of overcurrent devices used in these applications include circuit breakers and fuses. Circuit breakers offer the advantage of being resettable, while fuses provide fast and reliable protection. The choice between a circuit breaker and a fuse depends on factors such as the specific application requirements, coordination with other protective devices, and maintenance preferences. When selecting the overcurrent device, it is important to coordinate it with other protective devices in the system to ensure selective coordination. Selective coordination means that only the overcurrent device closest to the fault should operate, minimizing the impact on the rest of the system. This is achieved by carefully selecting the time current characteristics of the overcurrent devices to ensure that they trip in the correct sequence. Installing the overcurrent device as close as practicable to the transformer involves minimizing the length of unprotected conductor. This is typically achieved by mounting the overcurrent device in a switchboard or panel board located near the transformer. The conductors between the transformer and the overcurrent device should be sized according to their ampacity and protected from physical damage. Regarding the existing feeders, a detailed load calculation is necessary to determine the total load on each feeder. This calculation should include all connected loads, including motors, lighting, and other equipment. The load calculation should also consider demand factors, which are used to account for the fact that not all loads operate at the maximum rating simultaneously. After calculating the total load on each feeder, the conductor ampacity must be verified. The conductor ampacity is the maximum current that the conductor can carry continuously without exceeding its temperature rating. The conductor ampacity is affected by factors such as the conductor material, size, insulation type, and installation method. The National Electrical Code provides tables that list the ampacity of various types of conductors under different conditions. It is important to consider derating factors when determining the conductor ampacity. Derating factors are used to reduce the ampacity of conductors when they are installed in conditions that reduce their ability to dissipate heat, such as when they are installed in conduits with multiple conductors or in high ambient temperature environments. If the existing feeders are not adequately sized for the calculated load, they must be upgraded to conductors with a higher ampacity. The overcurrent devices protecting the feeders must also be correctly sized to protect the conductors according to their ampacity. The overcurrent device should not be larger than the conductor ampacity unless specifically permitted by the National Electrical Code. In addition to the above considerations, it is important to ensure that all electrical equipment is properly grounded and bonded to provide a low impedance path for fault currents. Grounding and bonding help to minimize the risk of electric shock and equipment damage in the event of a fault. Furthermore, regular maintenance and inspection of the electrical system are essential to ensure its continued safe and reliable operation. Maintenance activities should include, firstly, visual inspections of equipment for signs of damage or deterioration. Secondly, testing of overcurrent devices to verify their proper operation. Thirdly, tightening of connections to prevent loose connections and overheating. Fourthly, cleaning of equipment to remove dust and debris. In summary, properly protecting a transformer and its associated feeders involves careful consideration of the National Electrical Code requirements, accurate calculations, and appropriate equipment selection. By following these guidelines, one can ensure the safety and reliability of the electrical system. When adding new motors to the system, several additional factors should be taken into account. Firstly, the motor starting current must be considered. Motors draw a significantly higher current during starting than during normal operation. This inrush current can cause voltage dips and potentially trip overcurrent devices. To mitigate this, it may be necessary to use reduced voltage starters or other techniques to limit the starting current. Secondly, the motor overload protection must be properly sized to protect the motor from overheating due to overloads. The motor overload protection should be selected based on the motor's nameplate current rating and the applicable National Electrical Code requirements. Thirdly, the motor disconnecting means must be readily accessible and capable of disconnecting the motor from the power supply. The disconnecting means should be located within sight of the motor or be capable of being locked in the open position. Fourthly, the motor control circuit must be designed to prevent unintentional starting of the motor. This can be achieved by using safety interlocks and other control devices. Finally, all motor installations must comply with the applicable National Electrical Code requirements and local regulations. This includes requirements for wiring methods, grounding, and equipment clearances. In addition to the technical aspects, it is important to consider the economic aspects of the transformer protection and feeder upgrades. The cost of the overcurrent devices, conductors, and other equipment should be weighed against the potential costs of equipment damage, downtime, and injuries resulting from a fault. A thorough cost-benefit analysis can help determine the most cost-effective approach to protecting the electrical system. Also, it is essential to maintain accurate documentation of all electrical system modifications and upgrades. This documentation should include, firstly, the spill drawing showing the electrical system layout. Secondly, equipment specifications and ratings. Thirdly, overcurrent device settings. Fourthly, load calculations. Fifthly, short circuit current status. This documentation is valuable for troubleshooting problems, performing maintenance, and planning future upgrades. Remember, electrical work should only be performed by qualified and licensed electricians who are familiar with the National Electrical Code and local regulations. Improperly installed or maintained electrical equipment can pose a serious safety hazard. If there are any doubts or concerns about the electrical system, consult with a qualified electrical engineer. This detailed analysis and step-by-step approach should ensure that the transformer, feeders, and connected equipment are adequately protected, safe, and compliant with the National Electrical Code.